Okay, so now we are going to look at our box that is floating in water, or held in place by a spring, and we are going to try to figure out how far that spring is stretching to hold it in place. So we're going to have to use a couple models to do this. The first model is obviously the one for the whole section, this little section on buoyancy that we're using, and that is that the F buoyant force is equal to rho g volume submerged. And don't forget that rho is the density of the liquid, right? Not the density of the object. Sometimes we'll give you a density of the object, and sometimes people plug that in, and it's not it. It's the density of the liquid. That's what causes our buoyant force, right? This is going to result in a really dramatic increase in buoyant force. Sometimes you'll see, yeah, there's lots of videos on this on YouTube. Go to YouTube and Google cannonball floating in mercury, and you'll see lots of videos of like balls of iron floating in mercury, because mercury is more dense than iron, and so the buoyant force is gigantic. These bowling balls float relatively high in the mercury. It's really impressive. Okay, that's our first model. Our second model we're going to use is the mascot of mechanical engineering. Sum of the forces is equal to mass times acceleration. And our third model, can you guess what our third model is? We still have an element of this system which we're going to have to predict things about, right? And you guys have used this model before. Try to write it down before I do. And that is that the force on a spring is equal to a spring constant times x. And one of the things you'll learn is that this is not a great model. Most springs deviate significantly from this model, especially as you get to the end of the extension for the spring. The question is do you care, right? Cool. In other words, is it accurate enough for your needs? And it definitely is accurate enough for our needs here. So we know our spring constant. That's great. We know the density of our liquid because we are going to assume that it is water. This is water over here. We assume our box is empty, so this is air inside. And our box does not have any weight because it was not given. So cool. So we're going to start with our free body diagram. What are we going to pick for our free body diagram? We are going to pick our spring. Yeah. Nah, we're going to pick our box. Let's pick our box as our free body diagram. So our box has no weight, so there's no mass on it, but we do have a buoyant force acting on it, coming up like this, FB. And we do have the force due to the spring, F spring, acting here. And those two obviously must balance out, but we are going to apply our model first, and then we'll prove that that's true. So 1 to 2, we're going to pick just the y direction. Again, we have to draw in our coordinate system. Anytime we reference a direction, we need a coordinate system. So there's our coordinate system. So we're going to do F, sum of the forces in the y direction is equal to 0, is equal to our buoyant force, FB, minus our F spring, because our buoyant force is acting up and our spring is acting down. Cool. And then we're going to combine a couple other equations. So let's label these. We didn't label them earlier, so now this becomes 3 and that becomes 4. So 2 plus 3 plus 4 into 5 gives us that 0 is equal to our, we're going to substitute in our buoyant force equation. So rho g v submerged. And then we're going to subtract k, not kg, kx. Cool. Now the question is, we given our volume submerged? In fact, we are given our volume submerged. So our box is 1 meter by 1 meter by 1 meter, and it's submerged by a height h, which happens to be 0.25 meters. So we know G, we know rho, we know our V submerged, we know our spring constant. The only thing we don't know is X, which means we're done. We can solve for it. So if we do that, if we say 0 is equal to 1,000 kilograms per meter cubed times 9.8 meters per second squared times 0.25 meters cubed minus 10,000 newtons per meter times X. Now, if we solve for X, we find out that X is approximately equal to 0.25 meters, which is a happy little accident. We forgot our assumptions. We should write down our assumptions. Assume that fluid is at rest and our density is equal to a constant. And yeah, that's it. So a fun little question to ask yourself now, this box, right, is at rest. It's not moving, it's not rotating. And there are only two forces on it. What do we know about the line of action of those two forces, right? I'll let you pause the video and think about it. And then come back, assuming you're back. So what we know about these two forces is that they are collinear, right? They're collinear, so there's no force couple, there's no moment on this object, and since there's no moment on this object, it's not moving. If they were not collinear, then the object would rotate a little bit and find a new equilibrium. Cool. All right. So in class, we'll go over another instance of our semester-long design problem. This time, we're going to try to design how much empty float volume is required for the tower to float. So if you think about this tower, it's going to have to start horizontal, floating on Lake Erie, however long it ends up being, and then it's going to have to rise up from there as it goes towards the sky. But it initially has to float. And so given a certain linear density, so a density of kilograms per meter, how much empty float volume is required for the tower to float on Lake Erie? And we'll answer that question in class.